Hello, today it's my pleasure to talk about decimal floating point systems. We're going to start out with a two-digit decimal floating point system like that shown in the book. We're going to show how you accumulate round-off error as you do the various floating point operations. We're going to bring in the triangle law. We're going to do a simple example and a polynomial example where we show round-off error bounds. So this is very important in numerical analysis. And then we're going to extend it to a three-digit floating point system. So the two-digit decimal system that's in the book looks like this. You've got a sign, you've got a plus or minus 1 for a sign, you've got a first digit, a decimal point, and then a second digit, and then you have an exponent that goes with 10. The power of 10. So E naught is the power of 10 that you're going to be using for the particular number. So D1 is called the ones place, and D2 is the tenths place of the number. So the exponent is bounded between plus or minus between minus 9 and plus 9, so plus or minus 9. And we're going to claim this as a rounding system, and you'll see what that means in a minute. So whenever you see FL of x, that is the floating function where it takes a real value x and it floats it onto this format here. For example, if I take 104 and I quote unquote float it, then it's going to be 1.0 times 10 to the 2, or 100. This is rounding, so this one rounds down. So if I have 105 on the other hand, 5 and above, I'll round those up. So that rounds up to 1.1 times 10 to the 2, or 10 squared. So it rounds that up. So there's going to be a term that you really want to embrace, and that's called machine epsilon. And that denotes the accuracy of your system or the resolution of it. So this sets the precision of the given floating point system. Okay, so the first thing I want to kind of talk about is relative error, and that's to be differentiated from absolute error. So absolute error would be where you take the floated value that you get, and you subtract off the true value. And the relative error is when you take that in the numerator and you divide by the true value. So those are two different errors that you want to really understand. And if I kind of take these and rearrange them, I could get into a format that I'll use a lot. I'll use this a lot where I'm talking about floating an x, and that's going to be equal to x times quantity 1 plus the relative error of the floating point operation. So I'll use that a lot. Let's look at another example of this. Let's say I want to float pi. So pi, as you know, 3.1415926, etc. So if I float that, it's going to only take the first two digits, 3.1, and I'm not going to have, I'm only going to have an exponent of 0. So that's going to be my floated value. Now, if I look at what the relative error is of that, so I've got the floated value minus the true value divided by the true value, and I end up with, now the rows are, they are signed values, and here I get a minus 0.0132. And this notation here, the floated value of x, is an element of this this floating system, the two-digit floating system. So I denote that by F2. The x is coming from the real values, you see this blackboard notation from time to time. So that's the set of real numbers, and here we're talking about the set of two-digit floats. So if you look at what this row x is, it's the 0.01 and change. So the absolute value of that row x is going to be less than or equal to the machine epsilon. So that's an important thing to remember. All right, so we're talking about an infinite number of real numbers, okay? And we're going to map that onto a finite set of floating point numbers. It's always a finite set, no matter how fine, even when we go to binary floats, there's a finite set of floating point numbers that you're going to have. So that's called float. That's called floating it. And if you have a particular float number and you want to unfloat it, I sometimes call it unravel it. So you get back to having that real number, or a real number that's representing the floated value. So if you start with an x and you float it and then you unravel it, you won't get the original x that you started with. So let's say, for example, that we're talking about an x that's positive. So it's going to have this type of format when we float it. And if I take that same x that's positive, I want to think about it being normalized, and that's kind of a air quote kind of situation. So you normalize it. So that means that you kind of put in that same 10 to the E0, that whatever you would have had over here, you put that same one over here, and then that puts a non-zero first digit. So that's called normalizing it. Okay, so we want to think about that for a moment so that I can write this conveniently. So I've got the floated, this will be the relative error. I've got the floated value of x minus x divided by x. I've got them configured so that I can, I want to kill or cancel the 10 to the E naught, whatever the E naught is, it doesn't matter. So it's all going to be canceled. And I get really what I want in the numerator. Get this difference that I want to investigate further in the numerator here. So I'm going to focus on that. On the next slide, I want to tell you, if it's a rounding system, okay? So the difference between these two numbers, the absolute value of the difference between those two numbers has to be less than or equal to half of the 10th place, 0.1 divided by 2, right? So that's all you can have of the value. So I take this and substitute it in right here, and I'm going to get that the relative error. So I'm going to take that numerator that I have here and plug that in with the 0.1 divided by 2 times that, and I'm dividing by the true value. So now the true values are going to cancel, and this is going to establish my machine epsilon. So it's going to be 0.05, or half of the 10th, half of a tenth. That's what it is. So that's what it is for a rounding two-digit floating point system. So if you're rounding, if you have a rounding two-digit floating point system, and the machine epsilon is 1/2 of the 10th place. If you're going to do truncating system, then the machine epsilon is the 10th place, equal to 0.1. Okay? All right, so we're going to look at 3 different floating point operations. There's the float operation itself. There's where you add 2 floats together, and there's when you multiply 2 floats together. And add and subtract are analogous. Multiply or divide are analogous. So we're going to try to establish the bounds for these operations. So float, we've already looked at that with the pi, but let's look at it again. So we're going to say relative error is the absolute error divided by the true value, and we're comfortable to rewrite it that way. So no matter what real value you have, the relative error of that floating point operation is going to be less than or equal to the machine epsilon. So let's check it out. An example, the 105, we saw where the 105 is 1.1 times 10 squared, which is 110. So if I take 110 minus 105, that's going to be 5, divided by the true value. So I get 0.0476. Yes, that's less than 0.05. So that's a true statement, and it will be. Okay, so that is a floating point operation. You're just quote unquote floating a value. You can rest assured that the maximum error is going to be 0.05 for the 2-digit decimal floating point system. Okay, so let's look at floating point addition, and I'm going to start with 2 floating point values. So x is a float, y is a float, so they're representable as being part of F2. and then I'm going to add them. But if you notice, the addition of the two floats is not necessarily going to be an F2. It's not going to be representable by F2. So when I float the 155, I'm going to round it up, 1.6 times 10 squared. And if I look at the relative error, we're going to have the 160 is the result of the float minus the 155 divided by the true value, 155, so 0.0322. So in any case, the floating value, the floating point result of adding two floats together will be equal to x plus y, the true value, times quantity 1 plus the row of the error. And we know that we're going to have that being less than or equal to machine epsilon, which it is in this example. So remember that the x and the y in this discussion for addition, the x and the y are floats, but their sum is going to be a real value that you then have to float. Okay, so that's a little bit tricky to kind of convey, but it's a reality. Okay, so that's floating point operation. Let's take a look at floating point multiplication. So same kind of thing where I've got x and y are floats, and I'm going to think about their product will not be a float. So I'm going to have to float it, and the relative error that I would get would be less than or equal to machine epsilon. Let's do an example. 1.4 times 10 squared, and then for x, and then y is 1.6 times 10. So x times y is 2240. So when I float that value, I'm going to get 2.2 times 10 to the 3. So now when I look at the relative error, I've got the 2200 for the float, and then I've got the 2240 for the true value. So I'm going to end up with an error of 0.01, which is less than 0.05. So remember here, what I'm saying is that x and y are floats, but their product will be a real number that you then need to float. And that's what this is telling you. Okay, so bottom line, floating point error bounds. If you're just talking about the float operation itself, the absolute value of the relative error will be less than or equal to epsilon. If you're talking about an addition of two floats, that operation, the resulting error will be less than or equal to machine epsilon. If you're talking about multiplication of two floats, the result of the operation will have a relative error of machine epsilon. And what we do, quite frankly, at least what I do, is I just think about a sequence of operations, and I'll just call them out as row 1 will be my first operation, row 2 will be my second, onwards up to k. So where each one of these operations, whatever they may be, any given single one of them, the absolute value of it will be less than or equal to machine epsilon. Okay, let's talk about the heralded triangle law. Pythagoras would have been so proud of us. Let's say generically we have the absolute value of A is less than some value E. Let's say the absolute value of B is less than some value E. Let's say you have an expression A plus B. The triangle law says that the absolute value of A plus B will be less than or equal to the sum of the absolute value of A and the absolute value of B. So the first thing you can do is bring in these notions of A being less than E and B being less than E. So I can do a cascading less than or equal, and then I can sum it up. So I have the sum, the absolute value of the sum of A and B is less than or equal to 2 times E. This works with vectors or complex numbers. I use this often, this last one. I use that often. I'm going to use it here many, many times in the expressions for floating point round off accumulation. All right, so let's take a look at just a normal multiplication and addition type of sequence where I've got a function p, and it's going to be of two variables, x and y, and it's going to be 4 times x plus 5 times y. Now I'm going to be clear, x and y are floats. They are floats, and I'm actually going to use these values later on just to kind of give you an idea. But what I want you to embrace that this resulting operation of 4x plus 5y, that's not going to be a float. It's going to be a real value, and we have to kind of think about what the round off is going to be and what the bound for round off is going to be. Okay, so let's kind of write it out. So if I have float of my function, this float of my function, and I'm going to think about sort of the sequence of things. Well, the first thing I need to do is float that 4x, so I put that in. I need to float that 5y, so I put that in. And then I've got to float the sum of whatever I get. And so I'm going to end up with 3 operations. I've got the first one is going to be for the 4x. The second one is going to be for the 5y. And then the third one is going to be for the sum of the previous 2 terms. Okay, so look how I do it here. I know I've got to float the 4x. So I know it's equal to 4x times 1 plus rho 1, where my rho 1 is taking care of the round off error for that operation. I need to substitute for float of 5y, so it's going to be 5y times quantity 1 plus rho 2, where my rho 2 takes care of my 5y. And then I'm going to float the sum of those two, which is going to be that whole thing in the parens times 1 plus rho 3, because rho 3 is going to take care of that final sum. Okay, so I've got it almost to a point where I can work with it here and figure things out. So what I do is I distribute the 1 plus rho 3. I go ahead and distribute that in there. And then I take these 2 factors and expand those out. Take those 2 factors, expand those out. And then, if you notice, I take the 5y and the 4x, kind of pull those apart right there, pull those out. And I've got 4x times some product of rows, or some terms of rows. I've got the 5y times some terms of rows. Okay? So let's take that last line of the previous page and write it this way. I know that the 4x plus 5y, this is my true value. And I know that this is the result of the floating point value, and it's going to be a float, so it's the final representation of it. I know that. So now I want to talk about there's going to be a couple of big steps here, right? So I'm going to pull this over to the left-hand side. So now I've got my absolute value right there, or I'm sorry, absolute error. There's the absolute error. And then I've got the other stuff over here dangling. Let's see if we can work with that. So we know that these rows individually, the rows are going to be small, like for our 2-digit system, 0.05, right? So they're going to be small. But the higher order products are extremely small. So what I do is I neglect those. I neglect them because if I think about it, rho 1 times rho 3, the biggest it can be is 0.0025. So it's very small. It's very much less than 1. So you really just typically ignore those higher order cross terms, cross product terms between the various rows. You ignore those, and then it kind of simplifies for you a little bit. And you end up with 4x and times quantity rho 1 plus rho 3, and you end up with the 5y times quantity rho 2 plus rho 3. Okay, so let's take that from the last page. Let's kind of work on that a little bit. And I silently forget that I have those higher order terms that I've neglected. And what I'll do is I'll take absolute value of both sides. Okay, so now I'm ready to rock. Now I'm going to use the triangle law multiple times. All right, so I've got the right hand side here is what I start with, and I know that's going to be less than, because of the triangle law, I know it's going to be less than or equal to the sum of the individual terms absoluted. And then I can break those down again, less than or equal again to the sum of the absolute valued terms there. And now I get it to a point where I can split out these factors where I get the 5y, the 4x's times their respective rows. And then I remember that the rows individually are all each less than epsilon. So now I've got this bound of error, and I'm able to do cascading less than or equals where I know that the row 1 is less than epsilon, row 3 is less than epsilon, row 2 less than epsilon, row 3 less than epsilon. And then I can put it all together and factor out that common epsilon. And I end up with 8 times x absolute and 10 times y absolute. So that's the error bound right there, and it looks pretty intimidating at first blush until you practice doing this a little bit. Then you'll recognize some patterns, and let's look at before I go into that. Let's look at an example where I take the 3.1 times 10 to the naught, or just times 1, and then y is 5.5 times 10. Epsilon is 0.05. Let's see how this works out. So I know that 4x plus 5y, when I put in the values, I get a 287.4. That's my true value. And then floated, I'll need to do each one individually. So I take the 3.1 times 4 is going to be 12.4, and then I float that, I get 1.2 times 10. And then if I take the 5 times times 55, I get, what's that, 275, I guess, 227.5 times 10. And I float that, I get 2.8 times 10 squared. And then when I add these together, I get 292. And then I float that, I get 2.9. So 2.9 is a result of those successive floating point operations, 2.9 times 10 squared. Then when I look at the error bound, I've got 8 times absolute of x plus 10 times absolute of y, quantity times epsilon, and I get a 28.74. And if I look at, hey, I'm going to check, is this 290 and this 287.4, that's equal to 2.76, and yes, that's less than a bound, as expected. So that's an example where you see what happens as you sort of do the individual floating point operations and how you carry those forward, and you successively lose accuracy. Not that much in this example, but it can be. And obviously, if you try some other examples of x and y, you can approach the bound. Okay, so wanted to kind of show you, get you thinking that there is a little bit of a shortcut to declaring the bound, and it comes back to having a good understanding of the operations and the sequence of operations. So here, what we did is the first thing we did was multiply 4 times x. The second thing we did is multiply 5 times y, and then we sum those two terms. So that's why this looks a little bit symmetric here. There's 2's in both places times the original two factor pairs that we had. Okay, so this 2 that you had to give you the 10y, that 2 was because that you did the second and third operation. That's because of row 2, row 3, the multiply of 5y, and then the sum of that term into the final sum. This 2 that multiplied the 4x to give us the 8x of the previous slide, that 2 is because of the 4 times x, that very first operation, the row 1, and then the row 3 when you had to sum it to the other with the other term. So I know just from doing this a bunch that that was going to be the bound. I knew that from the get-go. Okay, so and the only reason this is symmetric here, usually it's not symmetric. The only reason it's symmetric here is because of the symmetry. We did the 4x by itself, and then we did the 5y by itself, and then we summed them. So it wouldn't have mattered if we had swapped those around. Okay, I want to take a look at my quadratic polynomial that I promised you. The example I'm going to look at has a constant coefficient of 1, a linear coefficient of -4, and a quadratic coefficient of +3. So if you go through and use the normal quadratic solution here, you'll find that the real zeros or roots are 1/3 and 1. I want to go and see how our polynomial stacks up to compute this. All right, so here's my polynomial. I've got my a0 plus a1x plus a2x squared, and I want to set up a Horner sequence. As I may have mentioned to you before, a Horner sequence of calculating the value of this polynomial. So you're able, with the quadratic, you're able to calculate the value of a polynomial with 4 operations. The first operation is where you take a2 and you multiply by x. So there's going to be a multiply. Row 1 is going to be a multiply. Row 2 is going to sum the linear coefficient to the result of the first one. So that's row 2. And then row 3 is going to be where you take the result of the previous step and you multiply by x. And then row 4 is where you add in the constant term. So those four operations, you're going to have a multiply, add, or 2 multiplies and 2 adds. You're going to be able to calculate the value of the polynomial. Okay, so I'm going to start. I'm going to just to make sure I declare this. My coefficients are going to be floats, and my x is going to be a float. All right, so I'm going to look at sort of what the I want to figure out what the error bound is going to be for this. Okay, so just like we did earlier. Okay, so I'm going to write it out in the row format here, and I'm going to remind you that the first floating point operation is coming from a2x times 1 plus row 1. So that's my first floating point operation. And I'm going to remind you for what to look for. Adding in that a1 now, and I'm going to float that. So I'm going to have the 1 plus row 2 to take care of that. And then the third operation is where I'm going to multiply by x again. And then I'm going to float that. So I'm going to have this all times 1 plus row 3, because row 3 is taking care of that multiplied by the second multiply of x. And then the very last thing is where I add in that constant coefficient a0, and then I float that. So I've got a good algebraic representation of the 4 floating point operations of my quadratic. I call this the Horner sequence, and it's easy to do that in a for loop too, as we will see. Okay, so again, that we're taking that polynomial and we're going to float it. That's going to be a float value, and remember that all my coefficients and the x value are coming in as floats, and this expression on the right side is what I call the row I error representation. Okay, so let's see what we got here. So we're gonna try to break this out. We're gonna take what I had showed and talked about on the previous slide, and I'm gonna try to break that out into the 1 plus row factors term by term. So I'm gonna have my a0 term, 1 plus row 4. I'm gonna have my a1x term times its 1 plus row terms or factors, and then I'm going to have the plus a2x squared times its 1 plus row factors. Okay, so I'm going to take the previous representation, and I'm going to think about how these higher order terms can be neglected. All right, so if I were to take all of this and then expand those four factors out, and take this and expand these three factors out. All right, so then I'm going to be able to collect or neglect the higher order terms and collect the terms that are going to be representing the true value. So there's going to be my true value. And then for the A naught, all I'm left with is the row 4. And then for the A1X, all I'm left with is the row 2 plus row 3 plus row 4, because all of the other higher order combinations have been neglected because they're going to be very, very, very small. And then for the A2X squared term, all I have left would be just the linear terms of row 1 plus row 2 plus row 3 plus row 4. All of the the higher order row combinations, combined factors are going to be neglected. So this is, I'm in pretty good shape here. And then what I'll do is I'll pull over, I'll kind of forget that this is an approximation, and I'm going to pull over my true value with my float. So now that's my absolute error, okay? And then I'm going to remember that my A naught row 4 is going to be less than A naught epsilon. I'm going to remember that my A1X, I've got row 2, row 3, row 4. That's going to be less than, each one of these is less than epsilon. So that's where that 3 comes in. So I recognize there's going to be 3 operations that contribute with this term. And then for the A2X squared, I recognize there's going to be 4 operations because each one of these is going to be less than epsilon. And I'm able to factor out that epsilon out of the whole thing. And now I'm in pretty good shape. And I have to remember that as I take the absolute values and the triangle law just being repeatedly enforced here, I'm going to have everything with absolute values. So I can't forget that. Okay, so this is where this coefficient comes from. That's where that coefficient comes from, and so forth. All right, so this is a transition from the full row representation to the approximation. You can make this approximation because the higher order row 1, row 2s, etc. are going to be very small. This is significant, so now you only have to worry about the first order rows. And this is significant. It sets that maximum error in the calculation. All right, so now if I'm pondering if this x is a root, then I'm thinking about that combination of the true value to be 0. So then what I do is I just worry about this. If that value is less than this, then it's going to look like a root. So I can use that. I can calculate that sequence using the Horner sequence, or calculate that value using the Horner sequence. And then I can calculate this value using a modified Horner sequence. And I call this an error. So when I take that Horner sequence and multiply by machine epsilon, I call that an error. And I note that if my x, when I do the floating point calculation of the polynomial, if that x is a root, if I can declare it as a root to within round-off error, this statement would be true. Okay, so kind of shortcut again to declaring the bound. You're going to have triangle laws that are just going to cascade. So in the polynomial, I'm going to have an A2x squared. You're going to have an A1x. You're going to have an A naught, each one of those being individually absoluted. And then this term sees 4 operations. So row 1, row 2, row 3, row 4. So it's going to have a 4 there. This term here sees 3 operations. it doesn't see that first multiply of A2 times X. So it sees row 2, row 3, row 4. And then this A naught term only sees that very last operation. So it doesn't get, this scalar is 1. It only has a 1 there. Okay, so that's kind of the shortcut in order to figure out what your error bound is, remembering that the first operation is A2 times X. The second operation is taking that, that linear term and adding it to the previous result. The third operation is taking the previous result, multiplying by X. And then the fourth operation is the final sum, where you're adding in the constant coefficient. Okay, I wanted to do a little bit of a sanity check here, just so that everyone's on the right page here. So we talked about how we can get this polynomial here, but don't forget to multiply by the machine epsilon. That's very important, and that's what gives you the error that we talked about earlier. If you forget the machine epsilon, you'd get a huge error, but so don't forget that machine epsilon. All right, so what I did is I took that polynomial and did some calculations using the 2-digit floating point, and then I plotted that out. So the 2-digit floating point is presented here, where I did the 2 digits, did the calculation, and then I unraveled it so that I could plot it. So that's the floating point of that polynomial. That's in blue. And then in red, I'm showing a Boolean that says whether a particular X is a root or not. And you can see there's a whole swath of X values that claim that it's within floating point round off. So that was quite interesting. So a whole swath of X values that looked like they were potential roots. So the takeaway here is that this 2-digit F2 system doesn't have enough resolution, quote unquote resolution, to quote unquote see the 2 roots that are there. Remember that one of the roots is, the true root is 1/3 and 1. Calculations make it look like those 2 are coalescing into a double root. Okay, so that's the 2-digit run. So I've got the script2.m if you want to look at that. So let's say we added more resolution and added another digit, a 3rd digit in our system. So now we're extending what we had earlier, and we're adding a D3, and that's going to be our hundredths place. Everything else is the same. And for example, if I take 104.4 and I float it with the 3-digit system, I'm going to get 1.04 times 10 squared. If I take 105.4 and I float it, I get 1.05 times 10 squared. So now the machine epsilon is half of that hundredths place. So I'm going to call this F3. Okay, so we're going to do, again, rounding so that where half of the hundredths place is going to be my machine epsilon. All right, so now when I do the 3-digit run, I do the same thing, and you can see how much smoother my unraveled sequence of floating point values will be. And then you can see that with the 3-digit, that it very much can capture the actual 2 roots. So there's a swath near 1/3, and there's a swath near 1. So I definitely see the 2 roots, and I can even polish it after that. Okay, so the takeaway here is that the F3 system does have enough resolution to quote unquote see the 2 roots. All right, so key points, key takeaways. Floating point calculations have round off, which accumulates. And the challenges that we see, I showed you for the F2 system and the F3 system, those are also seen when we look at binary. And I'm going to look at binary with you next in our next discussion. Okay, so, and the other takeaway is the more calculations you have, the bigger that error bound becomes. Okay, so hopefully you've enjoyed that and gained a little bit of more of appreciation for floating point calculations.